So in this lecture, we're going to talk about the properties of trigonometric functions. And the very first property we're going to discuss is the fact that trig functions are periodic, which means they repeat their values at a regular period. Now, let's look at a particular example. We're to calculate, without using a calculator, of course, the value of sine of 405 degrees. So if we were doing this, what we would figure out, would think of a unit circle here. Okay, so I'm just going to create a unit circle, and then I stop and think about where 405 degrees is, and I recognize that it's more than 360 degrees. In fact, let's stop and think. 405 degrees would be 360 degrees plus 45 more, wouldn't it? So the 360 degrees takes us all the way around, and then 45 degrees more would put us right here, and so we would get to this position. Now, the fact that we went more, and that's this angle right here only, not going all the way around, is the 45 degrees, isn't it? And so what we see is that the sine of 405 degrees is actually going to be the same as the sine of 45 degrees. When we recognize that, of course, then we know that that's the square root of 2 over 2, don't we? Now, and that's what we mean is once we, the fact that the sine function is periodic means that every time we make one revolution of the unit circle with our angle, either in a positive or a negative way, the values start repeating themselves. So the sine of 405 degrees is the same as the sine of 45 degrees. If we went around 2 revolutions and then 45 degrees more, that'd be 720 plus 45, wouldn't it? And so what's that, 720 plus 45? So if we thought about that, 2 times 360 degrees plus 45 degrees, well, this is 2 revolutions. Okay, and so and so it will leave us at a 45 degree position, and that's what, 720 degrees plus 45 degrees, which is 765 degrees. And so the fact is that the sine of 765 degrees is also the same as the sine of 45 degrees, because we just made 2 revolutions and then 45 degrees more. So in general, what we can really say is that the sine of, I'm going to write it a little bit backwards from what I just did. Well, we can say the sine of some angle theta plus n times 360 degrees, where n is some integer, is going to be the same as just the sine of theta. And likewise, the cosine of an angle theta plus however many revolutions extra that we have here, n times 360 degrees, is just the same as the cosine of theta. Now, those could also be written in terms of not degrees, but radians. And of course, 1 revolution in radians is 2 pi, isn't it? So what this would look like in terms of radians is the sine of theta plus 2 n times 2 pi. So that means we're making n revolutions, okay? And then going theta more, that's the same as the sine of theta, and likewise here. Okay. Now, that's useful when we have angles that we're calculating the sine and cosine of that are much larger than 1 revolution, or are larger than 1 revolution in a positive or a negative way. And so what we say here, by the way, is the period, and we're going to do this in radians, the period of the sine function and the cosine function is 2 pi. It means it repeats, we get repetition of values every time we make a revolution, a period of 2 pi. They repeat every time we go 2 pi. Or, of course, in degrees, 360 degrees. So here's the way we would see this put to use. Calculate without a calculator the cosine of 10 pi. Well, so what we need to think of here is, I have to be honest with you, I probably wouldn't do the problem the way the directions ask us to use, because the directions are actually going to say, use the fact that this function is periodic. Use the fact that cosine is periodic. Okay, that's probably what it will say. And that's probably not the way I would approach this problem. I would just stop and think, well, now, where is 10 pi? Well, if we start at this position and we go around 1 time, that's 2 pi. We go around 2 times, that's 4 pi. If we go around 3 times, that's 6 pi. Go around 4 times, that's 8 pi. Every time we go around, it's 2 pi more, isn't it? We go around again, we're at 10 pi, and so it leaves us right there. And so at that point, the cosine is, the whole idea is the cosine of 10 pi is the same thing as the cosine of 2 pi or the cosine of 0. Cosine of 10 pi is the same thing as the cosine of 0 radians, which is 1. It's just a matter of where we're left. Okay, we could also see something that says calculate, let's say the cotangent of 13 pi over 6. Well, the biggest problem is, here is a little bit of an issue. You know, we saw previously the way we would count this off. You know, we'd say, okay, there's 1 pi over 6, there's 2 pi over 6, there's 3 pi over 6, there's 4 pi over 6, there's 5 pi over 6, there's 6, 7, 8, 9, 10, 11, 12, 13. So it puts us back where pi over 6 is. And if that gets real out of hand, I mean, there's a lot of counting to do, and we could almost lose track. So what we could recall, what we could figure out in this case, is the fact that this position, one revolution here is 2 pi. And in terms of 6, that's 12 pi over 6. So what we could really figure out here is that the cotangent of 13 pi over 6 is the same as the cotangent of 2 pi, that's 12 pi over 6, plus pi over 6 again. And so we get the same result as finding, I'll keep saying cosine there, the cotangent of only pi over 6, because of the periodicity, if you will, of this function. But we did that by counting, and we've already dealt with these problems. So now how would we go further here? Oh, well, here's how we would go further. Because the cotangent, remember, is the cosine of the angle pi over 6 divided by the sine of the angle pi over 6. And we've got to remember what the cosine of the angle pi over 6 is. Well, let's come back and think about this. We know, okay, so here's roughly pi over 6. I'm being real rough here. We know the cosine of this angle is the first coordinate. And we know that that first coordinate is either going to be, because it's between pi over 6 and pi over 3, we know it's either going to be a 1/2 or a square root of 3 over 2. Well, that's pretty clearly not 1/2. So the cosine of pi over 6, oh yeah, I remember, it's the square root of 3 over 2. And then we look at the sine of pi over 6, well, that's the second coordinate of that point. And the second coordinate would be along the y-axis, and that does look like 1/2, and of course it is, roughly, and of course we're talking about an approximation just from my diagram. And so yes, we have square root of 3 over 2 divided by 1/2, which of course is the square root of 3 over 2 times the reciprocal of 1/2. And of course, that reduces just simply to the square root of 3. Let's do one more that illustrates this maybe even to a greater extent. And it's because we have such large numbers involved. So that's on the next page. Well, you see here we're needing to find the exact value of the secant of 37 pi over 6, and that's really the issue. Is I don't want to count 37 pi over 6s off, and so I'm looking for a way to think this through. Now, in terms of 37 pi over 6, let's just stop and think about this. 37 pi over 6 is the same as, 6 won't go into 37, but it does go into 36, doesn't it? So 37 pi over 6 we could think of as 36 pi over 6 plus 1 single pi over 6. Now, what about 36 over 6? That's 6, isn't it? That's a 6 pi plus pi over 6. And the secret to 6 pi is it's actually 3 times 2 pi. And the reason I'm pointing that out is 2 pi is 1 revolution. 6 pi is 3 revolutions. And so what this is really telling us is that 37 pi over 6, we go 3 full revolutions and then pi over 6 further. And so we can conclude from that information that the secant of 37 pi over 6 is the same as the secant of pi over 6. All we're doing is letting algebra count our rotations. We had 3 full rotations or revolutions, and then we went pi over 6 more. And so now to calculate that, of course, we need to use one of our fundamental identities, and that is that the secant can be calculated as 1 over the cosine of the angle. And from the previous example, we determined that the cosine of the angle was the square root of 3 over 2, cosine of pi over 6. And of course that means that we have 1 times the reciprocal of that divisor, which would be 1 times 2 over the square root of 3, but then we need to, of course, which is just 2 over the square root of 3, but then we need to rationalize. And so we rationalize in this fashion. When we multiply the numerators together, we get 2 times the square root of 3, and when we multiply the denominators together, we simply get 3. So in this case, the result is 2 square roots of 3 over 3. Okay. Well, I guess that's the idea about what we were wanting to accomplish here. But on the next page, I want to give you another set of information about the values, the domain and range of the sine and cosine function. Well, I've changed my mind about what I want to present here, so I hope you'll forgive me for that. I want to discuss the sine table, SIGN, for the 3 functions sine, cosine, and tangent. And what I mean by sine, SIGN, is do we expect the sine of an angle to be positive or negative? Do we expect the cosine of an angle to be positive or negative? Now, that's the sine I'm talking about here. And the first thing, and depending on where the angle is, see where the terminal side of the angle is. So first thing we want to do is name and remember that the names of the quadrants. This is quadrant 1. Remember we named them with Roman numerals. Over here is quadrant 2. Roman numerals. Down here is quadrant 3. And over here, of course, is quadrant 4. Roman numeral. Okay. Now, let me just draw a little reference triangle down here. A little reference unit circle. Because what I'm really thinking of is a unit circle there. I just don't want it to get in our way. So, in quadrant 1, remember, here's the deal. if we have a point, if we have an angle that leaves us at a position in quadrant 1, well, in quadrant 1, and we'll just pick out some point x comma y, and remember then the cosine of the angle theta, if theta leaves us in this position, then the cosine of theta is x, and the sine of theta is the second coordinate, isn't it? But in the first quadrant, x and y are both positive. See, both of those are positive. So what we know is if our angle terminal side is in quadrant 1, then the sine of that angle will be positive. And we know that the cosine of that angle will be positive. And we know that the tangent of that angle, since the tangent is sine over cosine, and both of those are positive, then this is also positive, isn't it? So that's useful information to us. Now, there's a lot of angles that would fit in this, but that would leave us in the first quadrant, but certainly some angles that would be of that type would be any angle that is between, we'll call the angle theta, 0 and pi over 2 radians. Now, any angle that leaves us in there, but certainly those angles leave us there. And of course, if this vertical would be where theta is actually pi over 2. Oh, and by the way, over here at this, right here is where theta is equal to 0. I didn't start that. And clear over here to the left would be where theta is equal to pi. And clear down here is where theta would be equal to 3 pi over 2. And then back to here would be where theta is equal to 2 pi again, isn't it? Okay. Now, in quadrant 2, see now if we're in quadrant 2 and we have a point on the unit circle, okay, where we're left with our angle, well, in this case, the first coordinate is going to be negative and the second coordinate is going to be positive, isn't it? Because we're going to the left, we're going up. And so that tells us that the sine of an angle that leaves us in here, well, that's the second coordinate. So a sine would be positive. The sine of theta would be positive if we're in the second quadrant. If we're in the second quadrant, the cosine of theta would be negative because that's the first coordinate. And so that's a negative value for that first coordinate, isn't it? And then because we know that the tangent of theta is the sine of theta divided by the cosine of theta, that's a positive over a negative, and so that would be a negative result. Now the kinds of angles that would leave us here would be angles that are bigger than pi over 2, but less than pi. Beyond pi over 2, but not to pi yet. Okay, well, let's continue to quadrant 3. Well, in quadrant 3, we're talking here, so if our angle left us at this position in quadrant 3, well, let's see. The first coordinate is negative because we're left of the y-axis, and our second coordinate is also negative because we're below the x-axis. So that means the sine and cosine values are both negative. So the sine of an angle that leaves us in the third quadrant would be negative. And the cosine of an angle that leaves us in the third quadrant would be negative. But the tangent of an angle that leaves us in the third quadrant would be positive. Because remember, tangent is sine divided by cosine, and that would be negative divided by negative, which is positive. Now the types of angles that would be in here would be angles that are bigger than pi, not 0, pi. So our theta is bigger than pi, and this is a theta. Well, I kind of bummed that up, didn't I? But also less than 3 pi over 2. Okay, those would be the angles that represent third quadrant positions between pi and 3 pi over 2. Okay. When we move to the fourth quadrant, you kind of get the idea already. Anytime our angle leaves us in the fourth quadrant, then we have a situation where the first coordinate is positive, but the second coordinate is negative. And so that would tell us that the sine of theta, being the second coordinate, is negative, but the cosine of theta, being the first coordinate, is positive, and the tangent would end up being negative divided by positive, which is negative again, isn't it? Now these angles are the angles that are greater than 3 pi over 2, but less than 2 pi. You kind of have to keep that in mind as we go around the unit circle. So this allows us to, let's go to the next page and answer a couple of questions. So we're given a puzzle, more or less. Name the quadrant in which the angle theta lies if we know these two pieces of information, that the sine of theta is less than 0 and the cotangent of theta is also less than 0. Now, of course, saying that the sine of theta is less than 0 is the same thing as saying that the sine of theta is negative. See, that's what that's telling us, isn't it? And also the cotangent of theta being less than 0 is telling us that the cotangent of theta is a negative number. Well, okay, let's stop and think here. This is the way I don't really have that table memorized so much as I just understand where it comes from. And so I'm thinking, okay, in terms of a unit circle, and we get this theta, and the sine of theta is negative. Okay, that's what we know. And the sine of theta is the second coordinate, isn't it? Okay, sine of theta is the second coordinate. And so the only time the second coordinate is going to be negative is here. It's either going to be the third quadrant or the fourth quadrant. It could be either one, but we have more information. And so the other information we have is that the cotangent of theta is negative, okay? Let's keep that in mind. But the cotangent of theta is calculated by finding the cosine of theta divided by the sine of theta. Now we know the sine of theta is negative, and we know the fraction is negative, see, because the cotangent of theta is negative. And so that tells us that the cosine of theta has to be positive, doesn't it? Otherwise, if the cosine of theta was negative, we would have negative over negative, which is positive, and the cotangent of theta is not positive. So now we know the cotangent of theta is positive. Well, see, here's the quadrant where the cosine of theta is positive and the sine of theta is negative. How do we know that? Because the cotangent is the first coordinate. Over here in this quadrant, this first coordinate would be negative, and so we can't have that. So we put those two pieces of information together and determine that theta lies in quadrant 4. Pardon me. So in this next problem, as you see, we're given some information that the cosine of theta is negative 1/5, and the sine of theta is 2 times the square root of 6 divided by 5, and we're to find the remaining trigonometric functions. Now the big issue here, of course, is we don't know what the angle theta is. We don't know that. But that's not really the issue at this point. We're just, whatever it is, we have enough information knowing the cosine of the angle and the sine of the angle to find the results of the other, when we take the tangent of that angle and the cotangent of the theta and so on. Now, it's not actually necessary in this particular problem, but we could decide where this angle theta lies, that is, where its terminal side is, because the cosine is negative, and that means it has to lie on the negative side of the x-axis, and the sine value is positive, so it has to lie on the positive side of the y-axis, and so the angle actually lies in quadrant 2, doesn't it? That's where it is, but we still don't know what the angle is. But it's really straightforward because we used the basic identities. See, we've already dealt with this kind of thing before, and okay. So, for instance, to find the tangent of theta, remember, as we said before, well, that's the same as the sine of theta divided by the cosine of theta. So since we know both of those values, it becomes just an algebraic manipulation. The sine of theta is 2 times the square root of 6 divided by 5. And the cosine of theta is negative 1 over 5. And so that becomes 2 times the square root of 6 over 5 times the reciprocal of negative 1 over 5, which is negative 5 over 1. And we get a nice reduction here and get a result of negative 2 times the square root of 6. Now, in a similar fashion, the cotangent of theta, as we've already learned previously, cotangent of theta is the same as the cosine of theta divided by the sine of theta. It's the reciprocal of the tangent as far as that goes. But you notice that tangent is sine over cosine, cotangent is cosine over sine. In other words, this is the same as 1 over the tangent of theta, isn't it? See, that we could use that. But let's go ahead and use the original idea. Cosine of theta is negative 1 over 5. And sine of theta is 2 times the square root of 6 divided by 5. And so that means we take negative 1/5 and we multiply by the reciprocal of our divisor. So that'll be 5 over 2 times the square root of 6. Well, there's a little bit more work to do here because here our 5's will cancel, but we're going to be left with negative 1 over 2 root 6. And I'm kind of scrunched on space here. So we would have to rationalize. Let me come back over here where I have more space now. So we'd have to rationalize that, which means we need to multiply on the denominator by the square root of 6 and the numerator by the square root of 6. So when we do that, we'll get a negative fraction, of course, square root of 6 in the numerator, and 2 times, now when we say square root of 6 times square root of 6, we'll get a 12, won't we? We'll get a 6. We'll get a 6. Not bad. And 2 times 6 is 12. So this ends up being negative square root of 6 divided by 12. That's our result for cotangent of theta. Okay, well, what have we not done yet? Oh, we haven't done the secant of theta, have we? The secant of theta. Well, here's what we remember. The secant of theta is 1 over the cosine of theta. And once we remember that, then all we have to do is replace cosine of theta then with its value, which is negative 1/5. And of course, 1 over negative 1/5 is just the reciprocal of negative 1/5, or negative 5 over 1. And so the result we get here is just negative 5. And I'm sure you can fill in those details. And the cosecant of theta, that's our last one. Whoops. Cosecant of theta. Oh, I did it again. I guess I just don't want to do this one, huh? Cosecant of theta. Well, we have to remember cosecant of theta is 1 over sine of theta. And once we recognize that, then we can replace the sine of theta in the denominator with 2 root 6 divided by 5. Okay? And so that's basically the reciprocal. So we'd say this is 5 over 2 root 6. But then we would have to rationalize, and they'd have root 6 over root 6 that we multiply by, and so our numerator will be 5 times the square root of 6, and our denominator will be 2 times 6. When we do that multiplication, we'll get a 12. And so that's the result we should get there. Okay, well, let's continue with more problems on the next page. Okay, a couple of things before I start. In the last problem, again, we were given values of the sine of theta and the cosine of theta, and from that information, we calculated the values of tangent of theta and cotangent of theta and so on, without ever knowing what the angle theta is. And that's not unusual. There's lots of times we don't know the angle but we know the results of taking the sine and the cosine and so on of that angle, or we have other information. And this continues in that setting. We don't know what the angle theta is, but we know that the sine of the angle theta is 5/13, and we know that the angle theta itself lies in quadrant 2. And the question ends up being, what is the value of the cosine of theta, just based on that information? Now, quite frankly, we haven't seen anything like this before, and it requires us to gather some more information. So I posed the problem before we were quite ready to do it. So let's postpone this for a second. There are 3 more identities. Now, we have these basic identities. That is, the tangent of theta is the sine of theta divided by the cosine of theta, and so on. But there are 3 more very important basic identities that we need to discuss. And so let me draw our representative unit circle, and let me just pick a position on the unit circle so we have an angle that leaves us at this position, and let's say that its coordinates of that position are xy, okay? And so what we know, and so the angle that we're talking about leaves us here. So I'm just saying that's the angle. I don't know if we go around 10 times or we go around once. If we don't go around any, we go directly there, where we go backwards, but that's where theta leaves us. And so we know that the sine of theta, which is that second coordinate, is y, don't we? And we know that the cosine of theta, which is that first coordinate, is x. But remember, this is the unit circle. We did this a while back. And the unit circle, the equation of this circle is x squared plus y squared is equal to 1. Remember, that's the x squared comes from x subtracting the center of the x coordinate of the center. And since the center is the origin, that would be x minus 0 squared, and so on. And the radius is 1, and we have the square of the radius over here where we have the 1. So anywhere on this circle, that relationship is true. Now, that means that what that tells us is that if we replace x with, since x is the cosine of theta, okay, since x is the cosine of theta, that would mean if we square the cosine of theta, and since y is the sine of theta, if we square the sine of theta, we'll get 1. This is called the Pythagorean identity. Now, we actually write that a little differently. Rather than writing cosine of theta in parentheses and sine of theta in parentheses, we get rid of the parentheses, and I'm going to put the sine value in front, and we rewrite that square over the sine so it doesn't look like we're squaring theta. See, sine squared theta means we're taking the sine of theta and we're squaring the result. We're not squaring theta, okay? And rather than writing cosine of theta in parentheses squared, we write this as cosine squared theta equal 1. This is a critical identity. This is a critical identity. Now, using that identity, so add this. I can't put enough asterisks here, okay? Add this to our list of things we've got to know. We just use it over and over. Now, given that information, okay, let's go further now. We're ready to deal with our problem. What is the value of the cosine of theta? Well, we're going to have to calculate it. But here's what we know. Now, this was extra, okay? Let's go back to our problem. We know something about this angle, okay? We know that the angle is in the second quadrant, okay? So the angle actually leaves us over here someplace, doesn't it? Excuse me. And in this second quadrant, what do we know? Well, we know that the sine of an angle in the second quadrant is positive. Well, yeah, we know that actually the sine is 5/13, which is positive, isn't it? And we also know that the cosine of an angle in this quadrant is negative. Now, we don't know the cosine yet, but we know because it's in the second quadrant, it's going to be negative. And that's what this is telling us. Okay. Now, here's the next thing we know. Also, we're going to use this. We know that sine squared theta plus cosine squared theta has got to be equal to 1. And we know the value of sine. So this really says, okay, we're replacing sine of theta, because remember, that's what we mean. Again, sine squared theta is a fancy way to write the sine of theta all being squared. And so we know the sine of theta, which is 5 over 13. What we don't know is the cosine of theta. So we don't have a replacement. That's what we're trying to find. But if we add those two together, we get 1. So now it's a simple operation. If we square 5 over 13, we'll get 25. We'll get 25 over 169. Okay? Plus cosine squared theta is equal to 1. Now let's remember, cosine squared theta really means the cosine of theta being squared. And if we solve for the cosine of theta, then what we're going to have to do is subtract this 25 over 169 from both sides, aren't we? So that's all I've really done is subtracted 25 over 169 from both sides. So on the left side, we have the cosine of theta being squared, and on the right side, we need a common denominator of 169, and so we'll write 1 as 169 over 169, and we're subtracting 25 over 169. So that leaves us with the cosine of theta all being squared. When we do that subtraction, 169 minus 25 is 144. Okay? Now, normally when we have something squared, see, normally we'd say, oh, okay, so the cosine of theta is either plus or minus the square root of this number, 144 over 169. But we know from above, see, we know right up here, don't we? Right here, we determined that the cosine value, because theta is in quadrant 2, the cosine value is actually negative. And so that's the sign that we actually have. Now also, the square root of 144 is 12, and the square root of 169 is 13. And so we have the cosine of theta is negative. We already decided that, 12 over 13. Now that's the big deal, and we used this, didn't we? That's a big deal. Now, from there, we could calculate the others, couldn't we? See, now that we know both sine and cosine, we could be asked to calculate the tangent. Now that we know sine and cosine, we could be asked to calculate the cotangent. Now that we know sine and cosine, we could be asked to calculate the secant. The issue here was coming up with the cosine. The rest of it's simple. And let's look at another challenging one on the next page. Okay, as you can see here, another challenging one. Given the cosine of theta is negative 4 over 9, and that theta is between pi and 3 pi over 2, find the value of the tangent of theta. So let's just kind of make notes of what we need to do, okay? So we need to find the tangent of theta. Now we do know that the tangent of theta is the sine of theta over cosine of theta. Okay? And we already know what the cosine of theta is, don't we? So you already know that this is a negative 4 over 9. So our job is to figure out what the sine of theta is. And if we can figure out what the sine of theta is, then we'll be in good shape. Now, what else do we know? We know that that theta is between pi and 3 pi over 2. Where is that? See, here is where pi is, and here is where 3 pi over 2 is, and so we're in the third quadrant. And in the third quadrant, the cosine of theta is negative, and we see that, doesn't it? It's negative 4/9, but also the sine of theta is also negative, isn't it? Sine of theta is also negative. Okay, well, that's important information. Now, the next, we haven't used it yet, but we do know that the cosine of theta is equal to negative 4/9. And we need, this is kind of the way I'm thinking of this, we need to know the sine of theta. And so what I'm doing here is I'm looking for a relationship. Look for a relationship, an identity, that involves both. The thing I'm looking for and the thing I know. And in this case, that relationship is sine squared theta plus cosine squared theta is equal to 1. Because if I replace cosine of theta with negative 4/9, the only unknown I'll have is the sine of theta, and I can solve for it. So that's exactly what we do here. We replace cosine of theta with its value, negative 4/9, in this identity. It's called a Pythagorean identity. And so now we begin to solve here, sine squared of theta plus, when we square negative 4/9, we get 16 over 81. Okay, and of course that's equal to 1. We subtract 16 over 81 from both sides. So we'll have the sine squared of theta is equal to 1 subtract 16 over 81. And then, of course, we need to create one fraction, so we'll say 1 is 81 over 1 minus 16 over 81. And what's that come to? What is that? 81 minus 16. Let's see. 71, 65. Is that right? I believe so. So we get 65 over 81 when we do that subtraction. Now, since sine squared of theta, you know, I'm not gonna rewrite it each time. I'm just having you remember that this really means sine of theta being squared. So that means the sine of theta itself would be plus or minus the square root of this side. But as before, and we already know that the sine of theta is negative from up here. We made that analysis a while ago, didn't we? So we're not going to use the plus portion of this. So what we know is the sine of theta is the negative of the square root of 65 over 81. Now, the square root of 65 we can't do anything about, but the square root of 81, we can't simplify it any further, but the square root of 81 is 9, isn't it? So sine of theta is negative square root of 65 over 9. Now, what was it we were trying to do? We were trying to find the tangent of theta. And we said, oh, okay, so now we're about to finish out. We know that the tangent of theta, that was the missing part, was the sine of theta. The tangent of theta being the sine of theta divided by the cosine of theta. Well, the sine of theta is negative square root of 65 over 9. And the cosine of theta is negative 4 over 9. And so when we simplify this, we would have a negative divided by negative, which is going to be a positive, isn't it? And we have a square root of 65 over 9 times the reciprocal of the divisor, which is 9 over 4. And things simplify nicely to be a positive square root of 65 over 4. So we didn't have very much information, but we did have enough to determine the value here. Now, once again, once we found the sine of theta, and we already knew the cosine of theta, we could find the value of any of the trig functions. We can just as easily now find the cosecant of theta, or the cotangent of theta, or the secant of theta, by knowing those basic identities. this identity, that's what this is called, this identity that we see here, sine squared theta plus cosine squared theta equal 1, is one of the most important things that you need to remember in trigonometry. Through all of the courses that you take when trigonometry is used, this is a very important idea. And remember, this came because from the idea that we were working in a circle. But and also remember what this really is telling us. This is a fancy notation. When we say sine squared theta, we really mean the sine of theta squared. We're not squaring theta, we're squaring the result of sine of theta. And of course, cosine squared theta is a special way to write the cosine of theta squared, of course, equal 1. Now, there's several things we need to know about this, but this leads us to a couple of other very important identities. And one of them, well, actually, here's what we're going to do, is we're going to take what we see there and divide both sides of this identity, or this equation, by cosine squared theta. That is, we're going to take the left side and divide by cosine squared theta, which is, of course, the same as dividing both terms by cosine squared theta. So we're just using the above identity, above equation, and dividing both sides by cosine squared theta. Now, that results in something else very special here. Remember that sine squared theta really means the sine of theta squared. And of course, cosine squared theta really means the cosine of theta squared. And so we have something similar over here, the cosine of theta squared divided by the cosine of theta squared equal 1 over the cosine of theta all being squared there. Now, the reason I've done this is we want to look at this very first term and recognize that that's the same thing as the sine of theta over the cosine of theta, and that fraction being squared. Because if we square a fraction, we square the numerator and denominator. So we're just going backwards from that. And then and then of course in this position, by the way, in this position we have the same thing in the numerator as we do in the denominator. So this is just a 1, isn't it? And over here, recognize this is the same thing as 1 over the cosine of theta, and that fraction being squared, because if we square a fraction, we square the numerator 1, which would just get 1. And the square of the denominator would be the denominator we have above. Well, the significance here is now we can look at this first term, sine of theta over cosine of theta, that fraction squared, but the sine of theta over the cosine of theta is the tangent of theta. And so that's all the tangent of theta squared plus 1 here. And then we recognize 1 over cosine theta. We've seen the identity that that's the same thing as the secant of theta. So here we have the secant of theta squared. Now, the way we actually write that is, as we did with the sine and cosine squaring above, we say tangent squared theta plus 1 equal secant squared theta. This is another very important identity, along with the one we have here. Now, I'm going to mention to you, I'm going to show you that we could have taken, another thing we could have done is we could have taken sine squared theta, plus cosine squared theta equal 1, and divided on both sides by sine squared theta. And if we did, then we would get something that looked like this. Now, in this case, in the first term, we have a 1, and in the second term, we really have the cosine of theta over the sine of theta, the fraction squared, which ends up being the cotangent of theta squared, which is cotangent squared theta. And here we have 1 over sine theta, the fraction squared, but 1 over sine theta is cosecant theta. So this is cosecant squared theta in this position. So this is another very important identity. The two above are more important, but this is a very important identity. And it's this middle one right now that's going to help us with our next problem that we'll do on the next page. Okay, we're given that the tangent of theta is 21 divided by 20, and that the sine of theta is greater than 0 or positive, and from that information we're supposed to find the cosine of theta, the sine of theta, and the cotangent of theta. Now, there's 2 or 3 things that are important for us to understand as we work through this. The fact that the tangent of theta generally, we know, can be calculated by calculating the sine of theta over the cosine of theta. But that does not mean, in this case, that the sine of theta is 21 and the cosine of theta is 20. And that's because that the sine of theta is always going to be a number that's between -1 and +1. And the cosine of theta can only be a number between -1 and +1. Now, why is that the case? Well, it's really a very simple idea, but it's very important that we recognize that we couldn't have the sine of theta being 21 because that's bigger than 1. And it has to do with the fact that these are defined in terms of the unit circle. So remember the unit circle. Well, okay, this is the value on the x-axis where x is 1, and this is the value on the x-axis where x is -1. And remember, the cosine of theta is the first coordinate of a point that's on the unit circle. Well, no matter where we are on the unit circle, that first coordinate's never going to be less than -1 or bigger than 1. That first coordinate's always between -1 and +1. And that's the reason we can make this statement. Now, on the other hand, this position up here is where y is equal to 1, and the position down here is why y is equal to -1. And remember, the sine of theta has to do with a position on the unit circle, and no matter where we are on the unit circle, the sine of theta is the second coordinate, and the second coordinate is never smaller than -1 nor bigger than +1. It's always between -1 and +1. So we can't make it is very important that we understand that the sine of theta and the cosine of theta are numbers always between -1 and +1. Now, they could be -1, they could be +1, but they can't be less than or -1 or greater than 1, in between. Okay, so we get that out of the way. Now, the fact that we do know the tangent of theta is sine of theta over cosine of theta, and we know that the tangent theta already, we know it's positive. So we know the tangent of theta is positive because it's 21 over 20. And the fact the sine of theta is positive, if the fraction is positive and the numerator is positive, then we know the denominator is positive also, don't we? So we do know that we conclude that the cosine of theta, although we don't know what it is yet, is greater than 0 or is a positive number. Okay. Now, we have to somehow get a relationship. The problem with using the relationship tangent theta is equal sine theta over cosine theta, the only piece of that puzzle we know is the tangent of theta is 21 over 20. We need a relationship where we know everything but one unknown, so that we can solve for that unknown. And this is where we're going to use the idea that it's always true that the tangent squared theta plus 1 is equal to secant squared theta. Now, the reason I say that is in this case, we know the tangent of theta. And let's just keep in mind, let's kind of keep in the back of our mind here, that the secant of theta is the same as 1 over cosine theta. So if we can figure out what the secant of theta is, we can figure out what the cosine of theta is. So here we go. We know what the tangent, let's come down here. We know what the tangent of theta is, and so we're going to use this identity and replace tangent of theta with its value of 21 over 20. And of course, so that's tangent squared theta there. Plus 1 is equal to secant squared theta. Okay? Well, now we know, well, we don't know, but we'll be able to calculate what the left side of this equation is. And so, oh goodness, let's see. I'm going to have to do some calculation here. So when we square 21, we get 441. And when we square 20, of course, we get 400. Now that we're going to need a common denominator, so I'm going to go ahead and write 1 as 400 over 400. And that's equal to secant squared theta. So I'm going to turn this around while I'm working on it. Secant squared theta then is equal to 841 over 400. And so the secant of theta is equal to plus or minus the square root. It's going to be one or the other. We just don't know which yet. 841 over 400. Oh, well, let's see what we've got here. Look back up here. Look back up here. Secant of theta is 1 over cosine of theta. And didn't we decide a while ago that the cosine of theta was positive? So this is 1 over some positive number, which means the secant of theta is positive itself. So this is the sign we're going to use. We know the secant of theta is positive square root of 841 over 400. So that means the secant of theta is equal to the square root of 841 over the square root of 400, which we already know is 20. That's where that 400 came from, basically, was squaring 20. Now the question ends up being, can we simplify the square root of 841 before we move on? Well, it so happens that the square root of 841 comes out evenly. 841 is a perfect square. The square root of 841 is 29. So this is 29 over 20, actually, secant of theta. Okay, now here's what we know. Look at this. We know that the secant of theta is 29 over 20, but we also know, the secant of theta, but we also know that the secant of theta is the same thing as the 1 over cosine of theta. And so 1 over cosine of theta is 29 over 20. Well, now what would we do about that? Well, here's what we would do. We'd say, okay, let's multiply both sides by cosine of theta. So when we multiply over here by cosine of theta, so what we need to do is get rid of the denominators, don't we? And at the same time, we want to get rid of the denominator on the right side, so we'd have to multiply both sides by 20. So let's do that here. Multiply by 20 and by a cosine of theta. So over here, we're going to multiply by a 20 and a cosine of theta. There's a little quicker way to do this maybe, but let's understand why we're getting this accomplished. So on the left side, the cosine of theta is going to be left over, and on the right side, the 20 is going to be left over. On the right side, the 20s are going to cancel, and we're going to have 29 times the cosine of theta. So what we're going to end up with is 20 is equal to 29 times cosine of theta. You might even say we could cross multiply, because the next thing we're going to do is we're going to divide out that 29 on both sides and get 20 over 29 is cosine of theta, where the cosine of theta is 20 over 29. Now, this could have been done much more quickly if we just recognize that the secant of theta and the cosine of theta are reciprocals of each other. Since the secant of theta is 1 over cosine of theta, that means the secant of theta is the reciprocal. And so we could have just said, oh, if the secant of theta is 29 over 20, then the cosine of theta is 20 over 29. In the future, we'll use that information. Okay, so we found the first value, which was quite a big job, but it was very important that we use the identity here to get as far as we've gone. Okay, this identity tangent squared theta plus 1 is equal to secant squared theta. Well, on the next page, let's calculate the sine of theta now. Okay, so on the previous page, you've just been there, but I've turned the page and so on. We had, we had cosine of theta is 20 over 29. And isn't that interesting? Isn't 20 over 29 a number that's less than 1? Yes, it is, isn't it? So cosine of theta is 20 over 29, and we need to know sine of theta, but we do know sine of theta is positive. That was told to us at the beginning of the problem. So now jumps in the next, the most important of the identities, and that's the fact that sine squared theta plus cosine squared theta is equal to 1. See, we need a relationship between those two functions and the ease. I mean, this isn't the only thing we could do, but it's something I want you to get very used to. So when we place cosine of theta with 20 over 29, and then we'll solve for sine of theta. So in this position, we have 20 over 29, but that's squared, since it's cosine squared theta is equal to 1. And then when we square 20 over 29, whoops, plus here. When we square 20, we get 400. And when we square 29, don't we get 841? Is that what we decided before? I believe so. Is equal to 1. So that means sine squared of theta is equal to 1 subtract the fraction, just subtract the fraction 400 over 841 on both sides. Well, then we're in a position that we need a common denominator again, so we'll write 1 as 841 over 841, and we're subtracting the fraction 400 over 841. So we have sine squared of theta is equal to 441 divided by 841. And so sine of theta itself then is plus or minus the square root of that fraction. But we know from above that the sine of theta is positive. So we have the sine of theta is a positive number, and the square root of 841, the denominator, we know is 29. And the square root of 441 is 21, I believe. Isn't that right? Yes, it is. So now we have the value of the sine of theta. On the previous page, we found the value of the cosine of theta. And the last thing we're supposed to do is to find the cotangent of theta. Okay, now we can go through the process of saying that the cotangent theta is the cosine of theta over the sine of theta. But notice this is absolutely the reciprocal. This is the reciprocal of sine of theta over cosine of theta. And sine of theta over cosine of theta is the tangent of theta. So this is actually the reciprocal of the tangent of theta. That is, tangent of theta and cotangent of theta are reciprocals. And we already know that the cotangent of theta, we already know that the tangent of theta is, what was it, 21 over 20? I believe that's right. And so all we need to do then to figure this out is, it's the reciprocal of those numbers. That would be 20 over 21, wouldn't it? So the cotangent of theta is 20 over 21, and we did that kind of in a little faster mode. Well, what I want to end with here is, actually on the next page I want to give a summary of some very important things for you to keep in mind, and that won't quite end what I want to do, but it will be, anyway, a big summary of things we've learned in this section and things we've learned in previous sections that are things that are absolutely critical that you know and you be able to reproduce throughout the rest of this course.